All right, yeah. Hi, everyone, and thank you for the introduction. So like you said, today I'll be talking about some recent work on the system Marius++ for large-scale training of graph neural networks on a single machine. Now, I want to start by considering an application that we're all probably familiar with, which is that of getting driving directions using something like Google Maps. For example, maybe I'm interested in how long it would take to drive from UW-Madison to Cornell before realizing that a flight might be easier in this case. But either way, most of us probably type in our destination and then take the suggested route without any question. But have you ever wondered how Google actually decides which route to suggest? Well, it turns out that as of 2021, Google Maps predicts the estimated time of arrival for route options using graph neural networks. They partition the road into segments, then represent each segment as a node in a graph, and connect adjacent segments by edges. Then they use graph neural networks on the resulting graph together with feature data about each node, like real-time travel information or traffic, to make predictions about the estimated time of arrival. So possibly without even knowing it, many of us have actually used the predictions of a graph neural network before in our daily lives. But it's not just Google Maps. Graph neural networks are everywhere these days. In fact, they are the state-of-the-art ML model over many forms of data, which are best represented as graphs. For example, ML applications over chemical and protein structures, social and biological networks, and knowledge graphs all use graph neural networks as the backbone. And of course, just like most areas of machine learning these days, real-world graphs are continuing to increase in size. For example, the Open Graph benchmark subset of the Microsoft Academic Graph contains hundreds of millions of nodes and billions of edges. And together with the feature data for each node, the storage overhead for this graph exceeds 380 gigabytes of data, making training GNNs on this graph a challenge. As such, a number of systems have been developed to help practitioners train GNNs over real-world graphs. And two of the most popular are DGL, which is developed by Amazon, and PyTorch Geometric. But let's consider what the options are for actually using these systems to train a GNN on this 380 gigabyte graph. Assuming we're using AWS, the simplest option for a practitioner is to use a machine with enough CPU memory to store the graph. For example, a P3.16x large, which costs $24 an hour. Alternatively, we might be able to distribute training across 7 or 8 smaller machines, but this would still result in a similar total training cost. And now this $24 an hour may not seem like much, but I can personally attest to the fact that even running these systems at a research scale, let alone an industrial scale, leads to tens of thousands of dollars in training costs per month. Thus, the basic question we're asking with Marius++ is, can we train a GNN on this graph, but using only a single P3.2x large machine, which is 8x cheaper, but which doesn't have enough CPU memory to store the full graph? And of course, we also need to train fast, otherwise we're not going to be able to take advantage of these cost benefits. And this is exactly what we were able to achieve by building Marius++ as a system with pipeline mini-batch training using the entire memory hierarchy, notably including disk storage. For this graph, Marius++ can actually train GNNs using this 8x cheaper hardware configuration and 8x faster, leading to a 64x cost reduction in training compared to DGL and PyG. But in order to achieve these results, we had to innovate and address two main challenges. First, given our goal of training on this cheaper hardware, we had to optimize GNN mini-batch training and mini-batch preparation and processing to make it as efficient as possible on machines with limited resources. And second, given that these machines may not have enough CPU memory to store the graph, we had to figure out how to utilize disk storage during training without bottlenecking throughput or hurting model accuracy. So for the remainder of this talk, I'm going to be focusing on how we address these two challenges. And I'm going to start first with the challenge of mini-batch preparation and processing, and then we'll move on to disk storage. And then finally, I'll conclude today with some experimental highlights comparing the three systems. Now, before we get into the details of GNN mini batch training, I want to highlight the key ideas to pay attention for in this section of the talk. First off, the key challenge that we'll see for training GNNs is that multi-layer GNNs require sampling multi-hop neighborhoods from the graph for each mini batch. Then I'll highlight that naive sampling methods for constructing these multi-hop neighborhoods can lead to lots of redundant work and thus lower training throughput. And finally, I'll introduce the techniques we developed in Marius++ to minimize sampling redundancy and reduce the time required for mini batch preparation and processing. So let's first begin with a bit of background and define the notion of a graph neural network. GNNs take vector representations for graph nodes and combine them with the graph structure to produce higher level representations, which can be used for downstream ML tasks. More explicitly, a GNN takes as input a base vector representation for each node I, which we denote by H superscript 0. And these can be node features, or they can be learned parameters part of the ML model. Then the GNN produces higher level representations for a node I, but by combining its own vector representation with the vector representation of its neighbors. And here the aggregation function is some parameterized model-dependent function that is learned and largely what distinguishes one GNN from another. And it's important to note that this neighborhood aggregation doesn't have to utilize all the neighbors of a node. Sometimes it's sufficient or necessary to sample subsets of neighbors as the graph becomes large. For example, here's a graphical depiction of a GNN. So say we want to compute H1 for the node Wisconsin. We can do this by aggregating its own base vector representation with that of its neighbors, Illinois and Madison. And in this case, the aggregation simply performs a summation over the three vectors and then multiplies the result with the learned parameter matrix W to produce a length 3 vector output H1 in this case. And of course, given this formulation, we actually have to go and store these base vector representations for all nodes in memory in a table which we're going to call capital H superscript 0, so that they can be accessed as needed for training. And some common GNNs, which you may have heard of that follow this structure, are GraphSage, the Graph Convolution Network, or GCN, and the Graph Attention Network, or GAT. Given this definition of a GNN, let's now turn our attention to the training process. For large graphs with many nodes, it's common for the storage overhead of the base vector representations to exceed the memory capacity of GPU devices. Thus, the basic training paradigm of interest for large graphs is mixed CPU-GPU mini-batch training. In this setup, the graph data is stored in CPU memory, and then mini batches of training examples are sampled from the graph, consisting of a subset of graph nodes or graph edges, depending on the learning task. But before we can transfer these batches to the GPU for computation, we have to sample neighbors for the nodes in the batch so that we have the relevant information to perform the GNN aggregation. And this mini batch preparation is a key step for GNN training and a significant difference from conventional ML models. Only once we have this neighborhood information can we then load the base vector representations from memory and transfer the batch to the GPU for processing. And the challenge here is that this training process is often bottlenecked by this mini batch preparation step because multi-layer GNNs require sampling multi-hop neighborhoods from the graph, and these quickly grow in size. So to see this explicitly, let's consider an example. Let's say that we're using a 2-layer GNN and the blue nodes A and B in the figure are part of our batch. Well, by using a 2-layer GNN, we know that we want to compute H2 for these nodes, and we know that these representations depend on their neighbors. Thus, to compute H2 for nodes A and B, we need to sample their neighbors from the graph. Assuming we're sampling a max of 2 incoming neighbors per node, we might sample nodes C and D as the incoming neighbors of node A, and node A as the only incoming neighbor of node B. But of course, the H2 representations for node A also depend on the H1 representation for node A, and likewise for node B. So we can also add these so-called self-edges to the diagram to signify all the layer 1 representations that are needed to compute each layer 2 representation. But we still can't actually compute H2 for either nodes A or B, because we don't know any of these first layer representations H1. These layer 1 representations also depend on the neighborhood for each of these nodes. So once again, we need to sample neighbors for these 4 nodes in the graph. For example, we might sample the neighbors as so. And notice that for node A, this time around, we may get the same 2 neighbors C and D, but it's also possible we could have sampled the neighbors C and E, for example, depending on the randomness involved in sampling. And only once we've completed all this neighborhood sampling do we finally have enough information to compute the desired output for the 2-layer GNN. At this point, we can actually go ahead and access the base vector representations for each of the unique nodes at the bottom of this computation graph, and then transfer all of this information to the GPU for mixed CPU GPU training. Now, the key thing to notice here is that this 2-layer GNN required sampling a 2-hop neighborhood for the nodes in our batch. And this is true in general. K-layer GNNs require sampling K-hop neighborhoods from the graph. And as we've previously alluded to, this is really the key challenge for mixed CPU GPU mini-batch GNN training. In order to prepare these mini-batches, we need to sample multi-hop neighborhoods, and these grow exponentially in size in the number of GNN layers. And constructing these multi-hop neighborhoods is definitely not cheap, because doing so requires randomly sampling large quantities of nodes and edges from the graph. But one thing we noticed is that this problem is actually exacerbated in existing systems because they perform a lot of redundant single-hop sampling to construct these multi-hop neighborhoods. For example, existing systems like DJL sample neighbors for all unique nodes in the frontier at each sampling step. In our example, we started by needing to sample neighbors for nodes A and B, and this led us to nodes C, B, A, and B. Then at this point, we completed the multi-hop neighborhood by sampling single-hop neighbors for each of these 4 nodes again. But a lot of this work is actually redundant because we had already sampled single-hop neighbors for nodes A and B in the previous step. And even if we had sampled different neighbors for nodes A, for example, the second time around, chances are some of them would still have been redundant. So ultimately, to construct this multi-hop neighborhood, we performed 6 total single-hop sampling calls, leading to 9 total sampled edges, not counting the self edges, but only 6 of these sampled edges were actually unique in this case. So with this in mind, a simple idea for more efficient mini-batch preparation and processing in Marius++ is to minimize the single-hop sampling redundancy while constructing these multi-hop neighborhoods for GNN mini-batch training. But of course, in order to do this, you need some way to track which nodes require sampling at each frontier. And we need an efficient way to construct, store, and process the resulting multi-hop neighborhoods. So to that end, in Marius++, we introduced the delta encoding of neighborhood samples data structure, or DENS for short, which tracks multi-hop neighborhoods using incremental deltas between each successive sampling hop. And together with efficient algorithms for constructing DENS on the CPU and using DENS on the GPU, this led us to 14x faster multi-hop sampling and 8x faster computation compared to DJL and PyG. So returning to our previous example, let's assume that we've already sampled the neighbors for the target nodes A and B. At this point, the DENS data structure contains the following information as shown. There's a node IDs array containing the target nodes, which we've defined to be delta 2, with the 2 coming from the fact that we're using a 2-layer GNN. And then there's a neighbors array, which stores their sampled neighbors. And since each node may have a different number of neighbors, there's also a neighbor offsets array, which tracks which neighbors belong to which node ID. Then at this point, instead of sampling single-hop neighbors for all 4 nodes to complete this 2-hop neighborhood, in Marius++, we minimize redundant sampling by first identifying the nodes which don't yet have any neighbors. And these nodes are easy to identify using DENS, as they're exactly the nodes in the neighbors array, which are not in the node IDs array. For example, in this case, it's the nodes C and D. And we define these nodes to be the delta increment that should be added to DENS, and then proceed to sample single-hop neighbors for them. And this is actually all the sampling that's required for this 2-layer GNN. The neighbors from nodes A and B in the first GNN layer are implicitly copied from the second layer to complete the GNN commutation graph. And the final delta increment, delta 0, which contains node E in this example, is only needed as input to the first GNN layer and doesn't require any neighbors for the computation. So in the end, we were able to construct the multi-hop neighborhood for A and B using only 4 single-hop sampling calls instead of 6, and by sampling only 6 edges, all of which were unique, instead of 9 as before. Now, I'll also note that while we have presented this simple idea here, there are a lot of important implementation details which we've ignored. And the main thing I want to say is that we made sure dense is amenable to optimize kernels for the GPU computation, and that our algorithms for constructing dense, like those for single hop sampling and this delta increment computation, can be parallelized across CPU threads for high performance. So now let's take a look at some experiments to see how mini-batch preparation and processing in Marius++ benefits from these optimizations. To start off with, if we look at the number of sampled nodes and edges in each mini-batch for real GNNs with a different number of layers, we can see that by minimizing redundancy, Marius++ samples fewer total graph nodes and edges to complete multi-op neighborhoods. For example, Marius++ samples only 1 million nodes and 2 million edges for a 3-layer GNN, while DJL and PyTorch geometric sample twice this amount. And this minimization of redundancy is one reason that the mini-batch sampling times for multi-layer GNNs in Marius++ are significantly faster than baseline systems. As we can see in this table, Marius++ is 3.7x, 14x, and 26x faster at sampling 3, 4, and 5 hop neighborhoods compared to DJL and PyTorch geometric. At the same time, these smaller multi-hop neighborhoods, together with the use of optimized GPU kernels, allow Marius++ to perform the GNN mini-batch computation faster than existing systems. For 3 and 4 layer GNNs, Marius++ is 8x faster than DGL and PyTorch geometry. And while all systems currently run out of GPU memory for 5-layer GNNs on the existing AWS GPUs, which only have 16 gigabytes of memory, these deeper GNNs may become more practical as GPU memory increases, with the top of the line GPUs currently supporting up to 80 gigabytes of memory. So in summary, in Marius++, we were able to reduce the multi-op sampling and computation times required for GNN mini-batch preparation and processing, which directly leads to faster mixed CPU-GPU training. And equivalently, this means Marius++ can also quickly train GNNs on cheaper machines with fewer compute resources, which unlocks the first piece of the puzzle for resource-efficient, large-scale training on a single machine. So let's go ahead and shift gears a bit and turn our attention to disk-based training. And just as for the previous section, I want to start by highlighting the main ideas. So first, I'll describe in general how the main challenge for disk-based training is to simultaneously achieve high throughput and high model accuracy. Then I'll focus on this challenge specifically and discuss a problem we observed, which is that naive policies focusing on just one of these goals can hurt the other. For example, greedy policies for fast training lead to reduced mini-batch randomness and lower model accuracy. And finally, I'll end this section with an overview of the flexible disk-based policies used by Marius++ to allow optimizing for both high throughput and high mini-batch randomness. But before we get into these details, let's first just remember why we wanted disk-based training in Marius++. Well, while the mixed CPU-GPU training that we discussed in the first part of this talk is great for graphs which fit in CPU memory, we also know that large graphs may exceed the CPU memory of single cheap machines that we want to use for training in Marius++. Now, as we mentioned earlier, there are two options for dealing with this situation in existing systems. First, we could simply scale up to a larger machine, which does have enough CPU memory to store the graph. Or we could scale out to a bunch of machines which together have a large CPU memory capacity, and then run some sort of distributed training process. But both of these options are expensive and require a lot of resources. On the other hand, in Marius++, our goal is to scale beyond CPU memory by incorporating disk storage into the training process. And disk storage is cheap, it can easily support graphs of many terabytes, and it's already part of the memory hierarchy on all machines anyway, so we might as well try to take advantage of it. But unfortunately, disk-based training is not just a matter of storing the graph on disk and then doing the same thing we did for mixed CPU-GPU training, i.e. reading and writing batches directly to the graph data on disk. Because such a training process would require randomly sampling training examples, their neighborhoods, and their base vector representations from block storage directly. And this is prohibitively expensive given the hardware constraints and properties. Instead, we need to ensure that the access pattern to data stored on disk consists of sequential reads and writes for high performance. But these conflicting data access patterns directly lead to the main challenge with disk-based training, which is that to develop replacement policies for moving data between disk and CPU memory and iterating over training examples stored on disk, which together lead to fast training, but also yield models with accuracy similar to that which would have been achieved if the whole graph was available in CPU memory. And the real challenge here is that these goals impose different constraints. Fast training implicitly implies structured sequential access to the data on disk, while high accuracy training requires mimicking learning with the full graph in memory, where mini batches and multi-op neighborhoods are randomly sampled from the full graph. Okay, so how can we try to tackle this challenge? Well, in our first attempt, we're going to store the base vector representations for the graph nodes on disk, but partition them into sequential subsets. And according to these node partitions, we can also group the graph edges into sequential edge buckets, where edge bucket ij contains all edges with a source node in partition I and a destination node in partition j. And then with this data layout, subsets of the graph can periodically be brought into CPU memory by sequentially reading partitions and their corresponding edge buckets. And whenever a set of node partitions are brought into CPU memory, all the pairwise edge buckets are also loaded into memory, and together they make up an induced in-memory subgraph. Such sequential access to disk is better suited for the hardware constraints of block storage. And then once in memory, we can go ahead and perform mixed CPU-GPU training on this induced subgraph. But in this setup, the training examples to create mini batches and their subsequent multi-op neighborhoods can only be sampled from the in-memory subgraph. The problem with this setup, however, is that our initial attempts to develop replacement policies for moving partitions between disk and CPU memory led to low accuracy models. For example, a greedy policy for fast training, which tries to iterate over graph edges stored on disk by swapping partitions one at a time in such a way that the new partition brought into memory allows for processing the most previously unseen edges, produces the results in this table. With the GraphSage and GraphAttention graph neural networks on the Freebase 15K237 and Freebase 86M graph datasets, disk-based training results in significantly lower model quality when compared to training with the full graph in memory. And the reason for this drop in accuracy is because the structured access to graph data from the greedy policy, while beneficial for high throughput, actually leads to successive mini batches with correlated training examples. So to see this problem explicitly, let's walk through another example. Consider that we have 6 partitions and 4 of them can be brought into memory at a time. Then we may start by loading partitions 0, 1, 2, and 3 and their corresponding edge buckets into CPU memory. Now let's assume that we want to iterate over all graph edges stored on disk once for training. So in a greedy manner, we can start by generating mini batches using all the edges between the 4 partitions 0, 1, 2, and 3, which are currently in memory. And these are the edges contained in the 16 pairwise edge buckets between the 4 partitions, which we'll denote with E1. Then once we're done with the mixed CPU, GPU mini batch training using these edges as the training examples, we can replace one of the node partitions in memory with one currently on disk. And then we can resume mini batch training using all the new edges in memory to create new mini batches. In this case, these are the edges contained in the 7 edge buckets shown in E2. And we can repeat this process by swapping one partition one at a time and greedily training on all new edges until we have generated mini batches for training using all the graph edges stored on disk. But now we can see, however, that the problem with this setup is that successive mini batches can have highly correlated training examples. For example, if we look at E2, all edge buckets, and consequently all edges assigned to create mini batches during this part of training, contain nodes from the partition which was just brought into memory, which is partition 4 in this case. Thus, the entire set of mini batches focuses on edges which contain only a small subset of graph nodes. And this lack of randomness in the order edges are processed each epoch biases the training of GNN models, which contain shared parameters that are updated during the SGD backward pass for every mini batch. And it's one of the key reasons for the accuracy drop we saw earlier. So in Marius++, our key focus was on developing policies which had enough flexibility so that we could simultaneously minimize I/O for fast training, but also so that we could maximize the randomness in the order training examples are used to create mini batches. And to do this, we developed new replacement policies for moving data between disk and CPU memory, which we call two-level replacement policies due to their use of physical and logical partitions. And we also decoupled the greedy processing of training examples from the replacement policy, and instead randomly processed training examples to increase randomness. And with these new techniques, we were able to reduce the gap between the model quality of disk-based training and training with the full graph in memory by up to 80% compared to our original greedy policies. So the high-level idea behind the two-level replacement policies is to increase flexibility by introducing another level of abstraction. Our disk-based training setup consists of the physical partitions stored sequentially on disk as before, but now we also introduced the notion of a logical partition. So each epoch, we randomly group the physical partitions on disk into logical partitions. And this occurs without any data movement. We only do this mapping in CPU memory, and that's all that needs to be maintained. We then move data between disk and CPU memory using these logical partitions. For example, if we want to iterate over graph edges, we can run the fast greedy replacement policy from earlier, which we called beta, on the logical partitions, resulting in a two-level beta replacement policy. As before, when logical partitions are brought into CPU memory, so are their logical edge buckets, which amount to all the physical edge buckets between the underlying physical partitions in memory. And adding this extra layer of abstraction allows us to separate the granularity of data storage and access from data transfer. And with these two partition levels, we can independently tune the size of the physical partitions and the amount of data swapped with the logical partitions. And it turns out that this flexibility is particularly useful, as we'll see with some results in a couple slides. So returning to our previous example, consider that we have the same 6 physical partitions as before, but now we group the physical partitions into 3 logical partitions, A, B, and C, as shown. And again, we assume the 4 physical partitions, or 2 logical partitions in this case, can fit in memory at each time. Then with this setup, if we want to iterate over graph edges, we can use the two-level beta replacement policy to generate 3 logical in-memory subgraphs by swapping logical partitions one at a time between disk and CPU memory. And these logical subgraphs correspond to the following physical partitions in memory at each point in the epoch. And because we swapped logical partitions between subgraphs, 2 physical partitions are actually exchanged each time instead of 1, as in the previous example, increasing the turnover rate of graph data. Additionally, notice that the new edges brought in for each subgraph don't need to be used greedily to create mini batches. Instead, in Marius++, we use a randomized policy decoupled from the replacement policy. To iterate over all graph edges on disk, it suffices to randomly assign the edges in each edge bucket for mini batch training to any in-memory subgraph which contains those edges. For example, the edges between nodes in partition 0 and partition 1 don't have to be used to create mini batches right away in the first part of the epoch E1. Instead, we can defer their processing until later, in this case E2, to help increase the randomness in the order that edges are processed with respect to the graph nodes. So hopefully this example provides some intuition for how the combination of two-level policies and randomized mini batch selection can lead to better distribution in the order training examples are processed. And of course, as was the case for dense, we've skipped over many details here. For example, while we know that we can use this two-level beta policy to iterate over graph edges on disk, a key remaining challenge is to actually decide how to best use the flexibility, i.e. how to decide the number of physical partitions, the number of logical partitions, and the buffer capacity so as to minimize I/O and maximize the randomness among all possible settings of these hyperparameters. And in our paper, we analyzed how each of these quantities affects training time and model accuracy, the latter of which we approximated using a model we developed termed the edge permutation bias. And we provide automated rules for setting the hyperparameters to maximize performance. And finally, while we mentioned this two-level beta policy by name for iterating over graph edges, Marius++ also contains two-level disk-based training policies for iterating over graph nodes, which we term the dispersed and sequential training policies. So before ending this section on disk-based training, let's look at an experiment comparing the two-level beta policy with randomized training examples to the beta policy alone on physical partitions directly and with a greedy edge processing. So across data sets and models, the flexibility of two-level beta actually allows for simultaneously faster training and higher model quality compared to the plain beta replacement policy. And for GNN models, by improving the randomness in the generated mini batches, two-level beta significantly improves model quality for disk-based training, reducing the gap to training with the full graph in memory by 80 and 40% for the GraphSage GNN on the two data sets here, respectively. However, achieving high-quality models using disk-based training is still an open challenge for some data sets and some models. So there's certainly room for continued improvements in future work. So that mostly concludes the technical content. And let's go ahead and finish by looking at how everything we've discussed today comes together for end-to-end training in Marius++. For our experiments, we compared Marius++ directly with DGL and PyG, matching model hyperparameters where possible, but tuning throughput parameters individually to minimize the runtime of each system. And we compared the systems on the node classification and link prediction tasks using the largest graphs available to us. And these graphs range in sizes from 86 to 122 million nodes, and from 338 million to 1.6 billion edges. And for models, we used the common GraphSage and GAT GNNs, possibly coupled with the disk-mode score function for the link prediction task where necessary. And we compared the systems by measuring training time, training cost, and end model quality. For our hardware setup, we used the AWS P3 GPU instances with V100 GPUs. And for baseline systems, since they require the graph data to be stored in CPU memory, we always chose the smallest machine with enough CPU memory for mixed CPU GPU training. And we allowed baseline systems to use multiple GPUs if applicable, but always trained Marius++ with only a single GPU. And finally, for Marius++ disk-based training, we always use the smallest P3.2x large machine which doesn't have enough CPU memory to store any of the graphs in our experiments. So looking first at a comparison for mixed CPU-GPU training on the node classification learning task, when the full graph is stored in memory for all systems, we can see that in the blue squares, that Marius++ labeled as M in the table, DGL and PyTorch geometric, all achieve similar model accuracy. But looking at the orange squares, we can see that Marius++ reaches this level of accuracy 3 to 4x faster than the fastest baseline, which is DGL in this case, even though DGL is using multiple GPUs and Marius++ is not. And as we've shown in the first part of this talk, the key reason for this improved performance is the faster mini-batch preparation and processing in Marius++, in part because we minimize redundant sampling in multi-op graph neighborhoods using the dense data structure. But Marius++ can also train these large graphs using disk-based training on a smaller, cheaper machine using our two-level policies, shown as Marius disk in the table or M-disk. And even with this disk-based training, Marius++ reaches a similar level of accuracy, 3 to 8x faster than DGL. In fact, the Marius disk-based training on the 380 gigabyte Open Graph Benchmark MAG dataset, which we've been seeing as an example throughout this talk, is actually faster than the in-memory training of Marius++ on this graph, because the neighborhood sampling and forward pass computations become more efficient when operating on these reduced in-memory subgraphs rather than the entire graph. And the key benefit of this disk-based training is that Marius++ is not restricted to expensive machines with lots of CPU memory to train these graphs. Instead, we can use these cheap machines, leading to 16 and 64x cheaper training for large-scale node classification. And similar results are true for the link prediction learning task. For mixed CPU-GPU training with the full graph in memory for all systems, Marius++ reaches the same level of model quality, 2 to 7x faster than baselines. And again, disk-based training support allows Marius++ to reach similar model quality on cheaper machines, while still training up to 4x faster than existing systems on the expensive machines with the full graph in memory. And this leads to between 14 and 18x cheaper training for large-scale link prediction. So I'll summarize by saying that Marius++ is best described as a system for pipelined mini-batch training of GNNs in a single machine using the entire memory hierarchy. And while building Marius++, we addressed two main challenges. First, we focused on optimizing mini-batch preparation and processing for multi-layered GNNs, which led us to minimize redundant sampling with the dense data structure and to 14x faster sampling plus 8x faster computation compared to existing systems. And second, we studied how to train GNNs with graph data stored on disk and realized the importance of minimizing I/O for fast training, but also the importance of maximizing randomness in the order training examples are processed. And this led us to the two-level policies for disk-based training and allowed us to significantly improve the quality of disk-based models. And finally, I'll leave you with one of the core principles for those of us who have been developing the Marius system, which is that we try to maximize the use of available resources before scaling out to more resources for the problem. And with that, I'd be happy to take any questions. So yeah, thank you.